Good afternoon. I'm going to talk about Bayesian estimation applied to covariate software reliability models. So software reliability growth models are models that we use to predict reliability as well as number of failures and mean time to failure. And then we also use covariate software reliability growth models, which try to improve these predictions by including covariates to the model, which are testing activities. Okay, so past research that used covariate models, they usually apply maximal likelihood estimation or expectation maximization and expectation condition maximization to find parameters, to estimate parameters to do model fitting and predictions. So the contribution of this paper is to apply Bayesian estimation technique to improve those predictions and improve the model parameters estimation. So here we have the mean value function of the covariate models. So that's how we predict the number of failures at time interval n. And also you have the p function, which is the probability of finding defects at time interval I. So in this p function, we include the Cox proportional hazard model, which are our covariates. So we have beta parameters, which is the coefficient of the covariate. So we have one coefficient for each covariate that we add to the model. And also we use hazard functions to this model. So the H over there is the baseline hazard function. So again, past studies used to use maximal likelihood estimation. So now we are using Bayesian estimation, which is just combining prior beliefs that we have with the log likelihood to estimate our parameters. So like I just said, the Bayesian estimation is combining PDF of a prior belief, of a prior distribution with the log likelihood. And we have sometimes informative priors. So for example, we can use beta, gamma, or normal distribution, depends on the range of our values of the parameters. And also you can have non-informative priors. So for that, we use Jeffrey's rule, which is just the square root of Fisher information of our parameter. So sometimes it's not easy to find mathematical formulas for that. So that's why you use Monte Carlo simulation, Markov chain. So it's an algorithm that approach the posterior distribution by simulating sample randoms of prior distributions. Okay, so we have two algorithms that implement the MMC and CMC algorithms. So we call Metropolis-Hastings algorithm is one of them. So it's accept every single new random state with a determined probability. And we also use Gibbs sampling, which accepts every new state using probability 1. So it always accepts the new random sample, okay? So after doing model fit using this estimators that we found, we're gonna do model assessment, which by measuring goodness of fit of the model. So we use sum of square errors, and we also use archive information and Bayesian information criteria. So to illustrate this approach, we are using a data set containing 17 intervals of failure count data. And now I'm showing the posterior distribution of 3 parameters because I'm considering 2 covariates to this model. So we have 2 betas to estimate, one for each covariate. And I'm also estimating B parameter, which is my hazard parameter coming from my geometric distribution. Okay, so we simulate using MCMC algorithm. Then we found a posterior distribution. And then you can take the mean or median and use that as our estimator for our model fit and predictions. So I'm showing now 2 tables. In the first one, we have a mixture of informative and non-informative priors. So for B parameter, which is coming from my geometric hazard function. So for the first case, we are using non-informative priors for that. And we are using informative priors for beta. We are considering normal distribution for them. And now we have the results that the mean, the standard deviation, and the lower bound and upper bound of the confidence intervals. And in the second table, we are using informative priors for every single parameter. So we are considering beta distribution for B and normal distribution for betas again. So we can compare the results and see that they are very close to each other. But the point is, using informative priors, we can converge faster. So the results are similar, but if you have prior beliefs, it's gonna converge faster. So the interesting part now is the graphs. So we have the model fit, right? So the solid line is our actual data. So it's our failure counts data for 17 intervals. And we have the model fit using maximum likelihood estimation, which is the dashed line. And we also have the model fit using Bayesian estimation, which is the solid line with the circles. So they are close to each other. You can see that. And also the gray area is the confidence interval of my Bayesian estimation. Okay, so of my Bayesian fit, actually. So we can see that they are pretty close to each other. At some points, the maximum likelihood estimation are closer to the actual data, but at some points, the Bayesian fit are closer to the actual data. However, all data points are contained inside the confidence interval of the Bayesian fit. So our model is conservative. Now we can see the failure intensity, which is the failure per interval. And again, the solid line is the actual data. The dashed one is the maximum likelihood estimation. And the solid with circles are the Bayesian. We can see now how the performance of the Bayesian estimation are much closer to the actual data. Okay, so using the failure counts, you couldn't observe that much because they were pretty close to each other. But comparing the failure intensity, we can see that Bayesian estimations are more precise than maximum likelihood. So now also I'm changing the hazard function. So before I was using geometric models, and now we have other 7 hazard functions over there. So it's just comparing the goodness of fitness of them and the runtime as well. So we can see that geometric model converge faster. However, using negative binomial or discrete variable of order 2 will have better goodness of fitness. So which model you should pick depends on the user. I mean, you choose which one is better for you. To conclude, so to sum up, we present the Bayesian approach to estimate parameters of covariate models. And we could see that using prior information, we can converge faster, achieve better results. And as future research, we can try to prove analytically the convergence of MCMC algorithm. And also we will try to optimize this approach for more covariate data. Then we can apply those into the covariate tool that we have, which is called covariate software failure and reliability assessment tool. This is the acknowledgement of my research. So it's supported by National Science Foundation, and I have a poster as well. So if you have any questions, we can talk later. Thank you.